Hi, this is Mr. Mack. What I'd like to talk to you about right now is the idea of limits and derivatives with the tangent problem. So one of the first things that we come up with is, what if we have something like y is equal to x squared, and we want to know the slope of the line that is tangent to the curve at some particular value, for example, at x equals 2. Well, now, one of the ways that we do this is we say, all right, let's just come up with a second point on the curve, and let's go ahead and consider a line that is secant to the curve, in other words, one that goes through those 2 points, and let's consider the slope of the secant. Now, first of all, let's draw a couple of things here. This would be the x value of the second point, and it would be some distance h to the right of 2. So to express this x value right here, it could be thought of as 2 plus h. Now, this y value would be, to find the y value for x equals 2 plus h, y is x squared. So this y value would be 2 plus h squared. Oops. And so the slope of this tangent line, of this secant line, I'm sorry, let's say slope sub sec, would be y2, which is 2 plus h squared, minus y1, which is 2 squared, over x2, that's 2 plus h, minus x, which is 2. Now, if we do some math with this, we would get 4 plus 4h plus h squared minus 4 over h. And notice we have 4 minus 4 here. That goes away. So we get an expression for the slope of the secant line to be equal to 4h plus h squared all over h. Now, our problem is if we let this line, this point, 2 plus h for x, get closer and closer to 2, when it's actually the same point, h becomes 0. And notice that this expression right here has becomes 0 over 0 when h is 0. But notice, algebraically, this is the same thing as h over h times 4 plus h. Now, so the slope of the secant line at any place except where h is 0 is 4 plus h. So if we look at this, and we're going to do more with studying with limits, but if we ask ourselves, what is the limit? What is the limit of h over h times 4 plus h as h approaches 0? We're actually going to get 4, because any place except when h is 0, this is 1, and any place where h is not 0, but if it's approaching 0, 4 plus h is getting closer and closer to 4. So what we're going to do is we're going to define the limit of the slope of the secant line as the 2 points get closer and closer to be together to actually be the slope of the tangent line. Now, you probably recall that this expression right here is what was called in Algebra 2 the difference quotient. F of x plus h minus f of x over x plus h minus x, or a lot of times in the denominator they just wrote h. And that's because this expression, the expression for the slope of the secant line as h approaches 0 becomes the definition of the slope of the tangent line. Even more than that, we're going to say that when the curves aren't straight, this gives us a function, another function, and it's derived from this idea of the slope of the secant line. So we're going to call this the derivative, and that's going to be the definition of the derivative. So for y is equal to x squared at x equals 2, the slope at that instance for the curve is actually 4. Now, let's go on a little bit more with limits, and what we're going to do now is we're going to take a look at the New York wheel. It's 630 feet tall, and actually it doesn't exist yet, apparently. I saw something about it's going to actually be open, perhaps, or it's projected to be open in 2016. But let's imagine that once it's built, we go and we ride in the New York wheel, and we decide right from the top of the New York wheel to drop a penny. And we're also going to have to kind of assume that the air resistance and all that kind of stuff isn't going to slow it down. Now the question we might ask ourselves is, how fast will that penny be traveling, say 6 seconds after we drop it? Okay. Now, I'm pretty sure you've heard about Galileo and going up in the Leaning Tower of Pisa and dropping a lead ball or an iron ball and a wooden ball off. One weighed a lot and the other didn't weigh that much. And the prevailing thought at the time was that the heavier one would go faster, but it didn't. They both hit the ground at approximately the same time. Actually, Galileo got in a little bit of trouble for that because they thought that was heresy. It's amazing where, if you see something that actually happens, you say, well, that's heresy. But anyway, let's get back to the subject. What Galileo discovered was that the distance, we'll call it S of t, the distance above the ground is directly proportional to some constant times the square of the time plus of course the original height of the object. Okay, now it turns out that if we're dealing with feet here, then the constant is -16. So we could say that S of t is equal to -16 t squared plus h naught, which in this case is 630 feet. I think I scrolled down a little too far. No, I didn't. Here it is, 630 feet. So, but I mean, this will tell us where it is or how high above the ground it is at that time, but it doesn't really tell us how fast it's going. But let's do that anyway. S of 6 would be equal to -16 times 6 squared plus 630, and just for good sake here, let's go ahead and put this in there. We got -16, calculator's using x, of course, x squared plus 630. And now we can go to vars, over to y vars, function y1, and then we can put a 6 in, and it tells us 54 feet. So S of 6 is 54. So it's 54 feet above the ground at that particular point. Now the average velocity that the particle has traveled is the total distance divided by the total time, but that doesn't really help us much if we want to know how fast it's going at 6 seconds, because that's at that instant. We know that before 6 seconds it wasn't going as fast as it is then, and after 6 seconds it's going faster. But one of the things we could do is we could say, let's take a look at the average velocity over a brief period of time with 6. In other words, the v sub av from 6.1 to 6 seconds would be s of 6.1 minus s of 6 over 6.1 minus 6, the difference in time. This is the total distance it's traveled in that tenth of a second after 6 seconds. This is the total time that it had to travel. And if we take that, we've got 54 minus, well, we don't know what that is yet. Let's just ask it. We can second enter and go back here. We'll do 0.1. And we get 34.64. So 54 minus 34.64 over 6.1 minus 6, which is 0.1. And probably it's just easiest to do this in the calculator. So we have, what do we got? We got parentheses 54 minus, I'm just going to say ands because that was the last thing we did, divide 0.1. And so we get 193.6. Now, that is not the velocity it's traveling at that instant. That's the velocity it's traveling on average from 6 to 6.1 seconds. And the units, of course, are in feet per second because our height was in feet and the time that we're using here is seconds. But now, let's do this. If we did s of 6 plus delta t minus s of 6 over delta t, that's t plus delta t minus t, and we looked at the limit of this as t approaches 0, delta t approaches 0, we could probably squeeze in on the velocity. Now, we could do some things to help ourselves in the calculator here. So let's try this. Y2, let's just do parentheses vars, y vars function y1 of x plus 6 minus, up. Sorry about that. Vars, y vars function y1 of 6, close the parentheses for the numerator, divided by delta t, which I'm using as x here. Now, if we go to second window, that allows us to set up our table. And we're going to go over to ask. And then we're going to go back to y. And I'm going to get rid of, not get rid of, but I'm going to turn off y1. So we're only going to get y2 in the table. Now, second graph gives us the table. Now, 0.1 is 2. Let's see what happened. Oh, 2 decimal points. 0.1 is negative 193.6. Oh, hang on here. Yeah, it would have to be negative because it's heading down. So the negative sign actually. Oh yeah. So notice here I've made a mistake. This 34.64 actually is here. That's s of 6.1. And this 54 is actually over here. So smaller minus larger is going to give us a negative number. So it should be negative 193.6. But now, what we could do is we could say, all right, let's try 0.01. So we've got s of 6.01 minus s of 6 over 0.01. And that tells us negative 192.2. Let's try 0.0001. And we get, actually, probably not actually 192, negative 192, but it's close. Now, we could also squeeze in on it from the other side. Let's try negative 0.1. We get negative 190.4, negative 0.001. We get, well, actually, we get negative 191.984. Calculator's saying already, well, it's close to what, negative 192. So what we're claiming here is that as delta t gets closer and closer to 0, as our 2 points get closer and closer together, the velocity of this penny 6 seconds after we drop it, neglecting wind resistance and all that kind of stuff, is 192 feet per second. Whew, wow. Okay. Now, that's the kind of thing that we're going to do in this chapter. Now, let's just recoup here a little bit. And the idea is this. If you have a function, f of x, and you want to know the slope of the tangent at some point x, what we do is we postulate some additional value h being added to x so that we get another point x plus h. This y value is f of x plus h. This y value is f of x. And so the slope of the line that is the secant through these 2 points is y2, that's f of x plus h, minus y1, that's f of x, over x2, x plus h, minus x1, that's h. I'm just going to write h because notice that x plus h minus x is just equal to h. Now, this we're going to define to be the limit of it. This is the slope of the secant, and we're going to define the limit as h approaches 0 of this to be the slope of the tangent line to the curve at x equals x. Yes. So that takes care of 2-1.